from point. Click. Yes. So today is basically the introduction to machine learning, and we will get into a bit of probability basics as well. And that is in order to get you appraised on what is this whole underlying objective of machine learning. So the primary point is something which we call as statistically informed decision making. Now where does statistically informed decision making as such have its root is what we are going to learn. And in fact, you can pretty much relate that the statistically informed decision making is the crux. So if a problem is so ill posed that you cannot make a statistical decision on top of it, then you cannot employ deep learning or anything as such. So it needs to be a very well rooted problem. Your data sets, your problem definition, your objectives and everything need to be pretty well defined in order to get that one. So today we will start with where does that imposition lie? What are the roots of those particular assumptions which we are putting into place? And then we will go on to how do you check that whether these conditions are satisfied, because that's the first part. First you need to understand whether your problem is solvable at all or not. Once it's solvable, then we will get into how do we solve it in a better way, faster way, more time efficient way, less energy consumptive way, and all of these different things. So I'll get back from this definition which we had discussed in the last class, but this is to get the rest of the class, because I still see a lot of new faces over here today. Now the whole task which we have over here is what is called as learning, and that's the activity to be done. Now whether the activity is happening or not is going to be measured in terms of a performance measure called as P, and that is very much glued onto whatever task T which you are performing over here. So if your task changes, your performance measure needs to change. It will not be the same. So a task and a performance, they are paired against each other. Now there is something called as an experience, and experience is what you are gaining over this activity of learning. So the more and more experienced you become, the better you become at doing a task. That's a pretty standard definition. So the more classes I am taking, the better I am getting in understanding this subject. The more tests I am taking, the more evaluated I am, and accordingly I know that what are my weaknesses, and I will be incorporating some tricks in order to get around my weaknesses. So that's what a computer program is also going to do over here. So essentially you will say something is learning only if its performance as measured in P over a task T increases or improves with experience E. So experience can be you look over the same thing over and over again, you look over multiple things but in one shot. It can be anything of this sort. So we will come into what is an iterative learning, what is a one-shot learning, what is a zero-shot learning, what are few-shot learning. These are concepts where you get to know exactly like can I use the same data over and over to do it again, or do I need to keep on changing data, or can I have a way in which that I have so much of data that I just look at every single sample point over here only once at a time and still I am able to do. And you can pretty much relate it to some of your own learning experiences as well. So when you are say learning to bicycle or say learning to walk, I mean most of you will not be remembering, in fact I also don't remember what happened when I learned to walk, because that is before our standard memory actually develops. But cycling is an experience most of us would remember, and the only thing which you remember is how you fell from your bicycling experience for the first time. And that's when you truly know, now I know exactly when will I fall, so I will not do that one thing which is going to make me fall from the bicycle. So these are stuff. Now for some people you would see that you might have fallen down from your bicycle only once in your whole life, and that was all. For some it's like they will still keep on falling. I mean they ride bicycles day in and out and still they would keep on falling. So they would need more and more of it. So it's again a property of the model. So you are a model in this case, and for us it will be machines which will be those models, and there will be certain properties of those models based on which they will either need to take more and more time in order to come to a very good performance, or maybe they just look at it once and do it. So if we demystify this whole thing, then you can look at it that this was one of those photographs which I had given out, and then I was asking you guys to identify. So today let's ask the other people in the class, what do you get to see in this very crappy projection? Yes, some human beings are standing, and that's it. This projector is really bad. Huh? Lights? No, I don't think that will work. So it's the luminous intensity of the lamp is really low, and I somehow think that it's near end of life now. So that I will get it resolved with the caretaker for this complex. I will try to get it resolved. Now, anyway, and in the daylight it becomes even bad. So that's me. These are few other people, and there is this circular thing over here. Let's decipher what comes up over there. Okay. So the first thing, if I ask a computer to actually say interpret this image in a natural language sentence. Okay. And then these are pretty much practical systems as of today. So when I started deep learning about 5 years back, these were still problems which we need to solve, blue sky problems as such. So images to text was not such a easily available solution 5 years ago. But in last 5 years, we have been able to make it pretty much to the scale where today it's a Facebook app. So you would see that if there is a photograph and your bandwidth is really bad, you will get a black box, a square box over there and some sentence written. Like this person, that person standing over here, or 3 people standing in front of a tree, these kind of sentences. And that's not something you captioned your photograph. In general, you don't caption your photograph 3 people standing in front of a tree. So, or say somebody in front of Taj Mahal or Eiffel Tower or the Leaning Tower of Pisa and all of these. And in fact, they can pretty much identify most of these landmarks. And that's in fact another big project. I will, at a point of time when we enter into computer vision, I will tell you the story about how we created a data set, crowdsourced way of creating a data set of landmarks of the world. And that's something which is called as functional mapping of this world. And by way of that, we have a much richer source of information in order to do it. And today, in fact, these techniques are so wide scale used that they have become a quasi-surveillance mechanism itself. Where are people, who are people, and you are there the primary person in the photograph, but if you are in a crowded place, there are a lot of other people who would also come in the photograph. And if there is a fugitive over there, this becomes a mechanism of tagging and catching where was that particular person who was otherwise untraceable from government agencies and how you find them out. In fact, that's a practical thing which happens. And a lot of companies which would otherwise provide you social media for free are not actually doing things for free. So you are actually doing things to make them earn revenue. So whenever you post a photograph, you are putting down a crowdsourced information in order to track a fugitive or in order to track what is happening down there in the world, which is needed by governments, which is needed by agencies in order to make down decisions in order to make this world a much more better place. So that's the larger scale side of it. So there is a social implication, there is a business implication, and it's not a very straightforward way as we look into it. So if we have this first problem of interpreting an image into a sentence, and a practical use case for this is, say, blind people. Now, all of us are visually gifted. All of our social media is also something which is designed specifically for visually gifted people. Now, if you don't have vision, how will you access Facebook? If this is a simple question. Do you think you will be able to access Facebook if you are blind? Try doing it sometime, like close your eyes and try accessing Facebook and then figure out what's there. Or you can in fact have a text-to-speech, on-screen text-to-speech translator on your Windows 10 mobile phones or Windows 10 PCs and try to do even that. It will really be hard. It's really a very horrible experience which comes out over there. Now, until and unless we have mechanisms by which we can enable scenes or visual images to be interpreted as natural language sentences, it makes it a big problem. So that's the problem which we are solving for here. Okay. So first and foremost, what it would do is this would break it down into some small segments over there. Say that these are important segments for me, and these are what are called as semantic segments. Okay, great. Now that it breaks it down, it can identify what is there in some of these segments, but it cannot identify everything over there. Now from there it goes over and then identifies some faces. Now that it identified human, it could identify faces over there. Then recognize some other things, which are these Great Wall of China's logo and Great Wall of China tower over there. So these are what are called as inanimate objects or in the background of other things. And then it finds out, it recognizes these human faces and then gets out, okay, if there is a crowdsourced repository or somewhere from where I can match faces, then I am able to identify who that person is. Now that I am able to do, I will be able to synthesize a sentence which says that. And pretty much the sentence says that Debdoot, Kim, Jung and Wang are standing behind the near the Great Wall logo, and the Great Wall Tower is behind them. That pretty much summarizes whatever is the primary content of this scene. Now this is not the only way that this sentence can be written. The sentence has its own 5-6 different ways in which we can write it down, and everybody has their own style. However, in whatever way you write it, it's going to convey the same kind of an information, right? And this information is good enough for us to understand. Now let's get into how it was doing it. That's the primary part, because we are not interested in what it did. The whole objective of this class was how was it done, and we need to learn from that. Now it would start with the first phase, where it breaks it down into some of these small blocks or chunks which are called as salient segments. Okay, there would be one part of computer program written down whose job is to find out saliency in an image and then find out the segments over there. Okay. Now I see a lot of you are busy scribbling. If there is something on the slide, you may not need to scribble, because I'm going to release the slides. I'm also going to release the video as well for this one. So other than a very important point which is not present on the slide, you may write it down, otherwise primarily focus over here. Okay, let's get more engaging. I want to release out stuff which is mundane and very standard, so that you can have an access to that later on. But let's get this more engaging, where you ask me a question. If you have a question, raise your hand, interrupt, and just raise your hand. I will figure it out and respond back to you. So now, first part is that it breaks it down into segments. Okay. Now how it does is a different part of it. We will get into that how as well. Saliency is also something which we are going to study. Next, it identifies these some of these objects, which will be called as an objectify pipeline over there. So what is that thing which is present in that segment over there? Okay. Next, what it does is once it has identified humans, so it can detect that there are humans because there is a face which looks almost like a human. Otherwise, a body like this, which has four limbs and 4 hind limbs, which is standing upright, that can also be an orangutan, that can also be a chimpanzee. Any of these things is pretty much possible. And if you make an orangutan, I mean, in general, how many of you have seen actual orangutans in life? A few people have seen it. I mean, they can pretty much stand upright. And in fact, a stouted person and an orangutan will have almost the same kind of a form factor. A geometric proportion is there. So that can get confused. The only way you can identify, one is from the fur and the other is definitely from the faces, if you look at it. Okay. Now, once it is able to do that, now it can, on the other segments which are present over there, it can go and actually start finding what are inanimate objects over there and recognize those inanimate objects. Now it's able to identify 2 inanimate objects from its list of whatever inanimate objects are present over there. There are others like trees and mountains and something, but that does not make any sense because it's present everywhere. That's not a key point for me to identify something. Now once that is done, now that it has detected these faces, it's going to recognize faces as well. And in today's world, that's not a tough job. So starting from Orkut, which was somewhere in 2005, to Facebook, which came around, what, 2010? Maybe, yeah. 8, I guess. I mean, I know, like, I finished off my engineering and Facebook was there that year. 10 is when Facebook came to India to start their office. This is what I very clearly remember. So there you are able to do, and today like 80% of the younger generation is there on Facebook. That's what the statistics over there goes. So if Facebook was a republic, then that would be the biggest republic on planet Earth. This is, now you can imagine if that's that many number of people who have their profile pics uploaded over there, then that becomes a very good surveillance mechanism. You can have a face recognition engine running on that whole database, and you can pretty much find 80% of planet Earth's younger people population on that one and recognize them. And to the extent that a lot of you will put down your geotags, you would put your phone numbers, you would put your location, your address, your email IDs, your affiliations and everything. And by that anybody can narrow down exactly on where this person can be physically found to the highest probability. Now that's good, bad, on both sides of it. So every axe has a good use and a bad use. You can either use an axe to axe a tree, which is bad for the tree and good for you, or you can use an axe to axe a man, which is bad for the man and bad for you as well. Because, I mean, you would get prosecuted after that. So once you have all of these, next comes the biggest challenge. The biggest challenge, you have objects which you have detected, you have some order in which you have detected objects, but then you will have to synthesize a sentence which can be inferred by a human being. So that needs to have objects, that needs to describe the relationship between the objects. It also needs to describe the physical relationship between objects, like what is in the foreground, what is there in the background, and all of these. Now that becomes a knowledge embedding problem in its own way. And once you are able to do that through a scene description module over there, you will be able to synthesize this kind of a sentence. Are we good with this? Are we good? Okay. So now, yeah, we will be having each block as modules over here. In fact, we will be, I mean, vision part, every of these block is going to come in vision. That's the detail. This is, you can pretty much take that this is one of those use cases which we are going to cover through the syllabus of this class itself. We'll come to that. That's in 2 slides beyond this one itself. Okay. So now there is a challenge. Okay. Now this challenge is a boon and a bane based on which side of the table you are sitting. Do you think this is the only way of solving the problem? Can there be another way of solving this problem? Can like some of these blocks come before other blocks and some blocks go here and there? Yes? So let's do one of those. In a parallel universe, we trunk out that whole pipeline and we try to create another different pipeline over here. So now, if I pretty much toggle the location of few of these blocks and then build up this whole pipeline, you can see that even this is good enough to solve that problem. So what you do is first you find out salient segment. That's obviously needed, otherwise you will not be able to start the process. Now on that first you detect humans. Then you push down whatever is not detected as human as well as whatever is detected as humans into this objectify. So that's going to find out, okay, verify whether this is actually a man and what are the other segments and what they belong to. Now that you know which were humans, you recognize humans on that one. Now whatever were those other objects which were left over there, which look like objects but you don't exactly know, you recognize those inanimate objects over there. And then you can say, okay, this is the Great Wall of China logo, that is the Great Wall of China Tower, all of this happens, and then you parse everything back onto the scene description. Because some of these modules are just independent of each other. And if it's a parallel process, then parallel process can be implemented in any sequence. It does not make any sense. I mean, both of these pipelines need to come together to this one and only then it can work out. The only place where you cannot change the ordering is salient segment cannot go on top, because that's the starting point. Scene description cannot come in between, because until you have everything done on the vision side of it, you cannot describe the scene. That's only to hinge. But in between, a lot of these blocks can be moved. However, the problem is that you cannot make this objectify go over here. Otherwise, you will not be able to detect. Until you detect objects, you don't know what is which inanimate object to recognize and which animate object to recognize over there. Okay. So do you think this is good or do you think this is bad? So how many people think that this is a good thing that I can solve a problem in more than one way? Can raise your hands. Okay, half of the class. How many of you think that it is bad that I can solve a problem in more than one way? One guy, raise your hand, raise your hand. 1, 2. And what happened with the others? Are you guys still sleepy? I mean, you need to vote in favor of some. You cannot abstain from voting. Abstinence from voting is abstinence from national duty. No, then you need to cast in favor of notas. You cannot just refrain. I don't know. Can also raise the hands. Still there are people who have refrained from voting. Okay, now let me get into a parallel part of it, and that's from the hat which I don as a guy who makes products for one day in a week. Okay, now you are in academia. For academicians, this is a very good thing, because now what that means is you can have a paper written with a title, yet another method of solving this old problem. So it's like I have a data set, I have a problem, I have a good computer, and every 6 months I will write another method and publish a paper, which is good enough to meet my academic requirements over here. For PhDs, you can pretty much write a thesis saying that 7 different methods of solving one single problem. 7 chapters and you get your PhD out over there. I mean, everybody is clapping. You have 7 methods of solving a problem. Okay, great. Now on the other side of life, how many of you are going to stay in academia? Can raise your hands. So you want to make a career in academia. How many of you want to make a career in industry? Okay. And how many of you would aspire to be a product manager, line manager in industry? A product manager or a line manager in industry? 1, 2. Raise your hands full. I mean. Okay. Yes. This is what I like. You are supposed to ask every single thing which you are not able to get. So a product manager is a person who is going to design. So when you are an engineer, you are going to write this piece of code, but that's not all of it. Okay. Somebody needs to give you the specification of what you are going to code down. Only then the engineer is going to code it down. Once you have coded it down, then you need to run some amount of tests on top of it. That is the job of the tester, who is going to run a set of tests called as unit test or defined tests and say that this is functioning under these conditions. Once that is done, you submit all of this, the code along with the test report, to somebody called as a QC manager, or quality controls. Now what this quality control guy typically would do is he is going to ascertain that there are some set international standards, which is if I am company A and I am company B, that we speak with each other. So today, say you clicked a picture on your Motorola smartphone. That saved an image in JPEG. You uploaded it on Facebook. Now this JPEG image, what Motorola has saved, should be in such a format that your Facebook is able to read that image itself. So that can happen only if both of them set onto a set of standards. They agree that we will follow this kind of a file standard in order to provide our data to be able to read and write. So this QC guy is going to handle all of this. Now the product manager is that guy who, for one single product, so one single product may be a Facebook photo viewer. So there is one guy who handles everything associated with this one thing. So including the whole life cycle of this one. So line managers are, say Facebook has a photo app which works on mobile, which works on desktop, which works on Ubuntu's, which works on say browsers as well directly. So this guy is a line manager under whom you have multiple product lines which have more or less a similar kind of a convergence, and all of them are separately built. So this is a typical organizational structure. So now are we clear about the product manager's role? Okay. Now if you are a product manager and there is your business manager, who is the guy who has been given this task of bringing in money. So he will say that if you make me this and give it to this guy, then we can make this much of money and then I will pay you this much of salary. Okay. Now this business manager comes and gives it to you, and then you will have to tell him exactly how much will it cost. Simple thing. In order to make a photo browser, how much will it cost? This is the simple job which is given to the line manager. He will eventually get back to every single product manager and say, okay, you make it for Android, you make it for iOS, you make it for Chrome OS, you make it for a Windows 10 app, you make it an Ubuntu app, and you make a browser based thing. So there are 7 people whom he is going to ask, 7 different teams. Each team is going to give their cost estimates over there. Now say that this was a problem statement which was given by the business manager over there, saying that you have to make something which will take in a photo and generate a sentence out of it. It should work on Android, it should work on iOS, it should work on Windows 10, it should work on, and as a Ubuntu app, it should work on browsers and all of these different modes in which people communicate. So you are going to give them the cost, and you have to make something which is the best, or at least the most workable solution over there. It should not falter down. So how will you estimate the budget? So budget is going to be how much time is it going to code each of these blocks. Code, test, certify, deliver. These different parts of it. Okay. Now, look at this whole thing. It's going to take some fixed amount of money for coding each of these blocks and delivering it out. If there are this whole pipeline is something which this product manager, this technology guy, and then eventually the product manager is going to give down to a line manager. And in general, most of the pipeline should be of a similar order, other than there being some intrinsic restrictions in the operating system itself or platforms on which you are deploying it out. Now say that there is one way, second way, third, fourth, fifth, sixth, all of these different ways. So where will the cost increase? Where do you think the cost will increase if there are multiple ways? One is to compare them, first is to code them. This pipeline also has to be coded, right? Because everybody's input, output, all of those formats. So when you write a function, you have a set of inputs, you have a set of outputs, but then say my Python function is going to take a numpy array and generate a file, and in the other case, if my input is numpy array and output is also supposed to be a numpy array, then there are two different ways. I mean, I cannot just use one function for the other. I will have to recode the whole function over there, though internally it might be doing the same thing. Now the point is, if I have more than one way of doing it, then that is just escalating my cost, because I will have to implement each, check it out, then my QC guy is the final guy who says, okay, pick this one only. That is what we deliver out to the client. So that's going to escalate my cost. Now for an industry, this becomes the biggest problem. So if you have more than one way of solving, then your budget typically inflates. Now if I ask you this problem, do you think that the number of ways of solving this one is a countable set? So are we clear about countable sets? Okay, are we clear about infinite sets and finite sets? So if I tell something like, is it a countable but infinite set? Are you able to understand what that would imply? What would that imply? What do you think? A countable but infinite set. The set of all integers is a countable and infinite set. So essentially you can count. So you can individually identify every single solution over there, but the total number of solutions you cannot bound it. You don't know what is the total number of solutions which exist. Now for most practical problems, the solution space is actually a countable and infinite set. So for academia, it's always good. That's why we love to stay in research, because I know that I just have to scratch my brain and I will have yet another method of solving this problem. But then for industry, that is a problem, because every time I come with yet another method of solving this problem, that just escalates out the whole budget over there. Now apparently it turns out that this is not the only place where this problem exists. In fact, if you look into one of these blocks, let's consider this detect humans as one of the blocks in which let's look into what can be done. So one way would be that I have this small patch which comes to me, and I need to say whether there is a real human in that patch or not. Now once I take that one is I can use some of these features, classical computer vision type features, histogram of oriented gradients, wavelets, local binary patterns, and you get down a set of numbers which come down to you. Now if I project these numbers onto something which is called as representation manifold, I can find out what are my body parts. So these are separate pipelines itself. Okay. Now that I am able to find my body parts, I am able to identify that there is a face, there are two hands and there are two legs over there, and this is what is present. Now that this is present, I can use some sort of a geometric distribution between them, like this is the length of the hand, this is the length of the legs, and this is the difference between them. This is the ratio between the length of the leg and the distance between the hand and the leg. So that will be something which can define the skeleton of what will be a human being. Now that as a distance measure can get onto something which is called as a manifold. So every single point over here is associated with this total distance measure for a human being. So if a point lies on this kind of a Swiss roll surface, then I say that's a human being, otherwise it's not a human being. Okay. Now that I am able to do, I should be able to say that there is a human being, and that detects a human being very clearly over here. Do you think this is the only way we can solve it? No. by now you got the trick. Like anytime I ask you the question, this is the only way can you solve it, you would say no. So can you throw some other ways in which you think you can solve it? You can put random guesses. I am not asking you for technical jargons. Just think. I have a picture of a human being. How can I find that this is a human being in some other way? Yes. Okay, you can recognize with the face. If the face looks almost like a human, then you say it's a human being. Great, good answer. Any other ways? So it's like you take these human being and you have sort of like average value of pictures of all other human beings and you try to compare. Whichever has the minimum mean square error, you say that this is a human being. Okay, yes, that's also an answer. If there is somebody who doesn't wear a shirt. I mean, you can have people from Middle East who have a cloak to wear. So they don't wear typically a shirt in which you would be finding them. Or you can get from where? From Padmanabhaswamy temple in Trivandrum, where you cannot wear an upper body clothing in order to enter the temple. Or if you are wearing a dhoti, then how will it happen? It's not a trouser. There will be those things. So what you can give an answer over there. You will have one set of all pictures of people who are wearing dhoti, one set of all pictures of people who are wearing trousers, one set of people who are wearing lungis, and then you just compare. If it matches with one of them, it's a set segregation problem, nothing more than that. You can do that. Okay. So let's mix all of these suggestions, and then we come up with another method, which is something like this. You have this picture over here, and then what I do is, I do something which is called as a chroma clustering and a posture realignment. So what this chroma clustering is going to do is, the color of clothes and the face is very different from the background. Now the background is green, which by virtue of this projector is not at all visible to you guys. So you will be very easily able to segregate them. Okay. So that's called as chroma clustering. Based on color, I am just clustering everything. This belongs to one cluster, that belongs to another cluster. Now people will be standing in different poses. So one is, this is my upright straightforward pose. I can stand like this. I can like pretty much be like this. I can be like this. I can, and then a number of Michael Jackson poses as well. So you have the moonwalk pose, you have that 15-degree incliner pose or something over there. He used to incline in a weird way. So you need to realign those things as well, and that is what is called as a posture realignment problem over here. So once you are able to do that, you will be getting something which looks like this, which are called as silhouettes. So these are shadows of human figures. Okay. Now a human is going to match into any one of them. That's the point which you were telling, like I will have something and it will, if it matches down, or your mean square error, everything is going to be on that one. Now this error which I am calculating, like this thing matching to one of these, and whichever out of this whole set has the minimum, that is my distance measure. Say I take it. That would again form some sort of a distribution over there in a space of distance measure. Now if my distance is somewhere on this point set of cloud, a cloud of points, which is also called as a point cloud, you can also call it as a manifold if you feel like. We'll eventually get into definitions of what is a manifold and what is a point cloud as well. Don't overstress yourself. So a point cloud is just a cloud of points, and that's a discrete representation of something called as a manifold. A manifold is basically a surface, one lower dimensional surface in a higher dimensional space. So if I have a 3D space, which is this, any surface can be a 2D thing, but a 2D thing does not mean that it needs to be a flat plane. Plane is one surface. You can have a curved surface as well. So any curved surface has 1 degree of freedom, which is lesser than the degree of freedom in 3D space. Okay. So, and manifold as a name comes from, have you seen those Victorian era movies where the judge wears a wig? Pirates of the Caribbean. Right. So the judge wears a big wig. Now that wig is a fold of folds. So essentially that is folded and then it's again twisted and folded, like the filament of a tungsten lamp. Okay, so it's a twist of twisted thing kind of a thing. So that's what is typically called as a manifold, and manifold gets its name. So these kind of folded structures, these kind of surface structures in a lower dimension is what is typically called as a manifold. So if it lies on this manifold, then I can say that this is a human being. Yes? Yes, the point is that the silhouette of an orangutan and the silhouette of a human being is generally going to be quite different. The reason is because, I mean, my waist might match that with an orangutan. I mean, still may not match, I'm pretty sure. So, but the orangutan's waist is really, really wide, and the other point where typically you will have a point is that this last point of the front, the four limbs of a orangutan are significantly longer. It's almost of the same length as that of the hind limbs. Now, as a result of it, for most orangutans, you will see that this finger actually comes to the knees. For humans, that would come somewhere in between this part. So we will have it over here. That's the difference how these systems don't fail for orangutans. No, his problem is with the silhouettes. Because in the black and white, you don't get to see anybody's clothes. Hey, but there were some movies in which they show orangutans also wearing clothes. I forgot. There is some comic movie I was watching the other day. Okay, so you can get it confused even with bears as well. There was one of these movie of that teddy bear who wears clothes and becomes a friend with some other guy. Ted, yes. So that can also be confused with that of a stout person as well. Yes. Yes, they can be partial, yes. They will be challenging situations. So we will now have to design systems. So this is the work of that tester in a company. What he has is, he has a set of all of these different kind of things which can come, and then he says that this is able to do tick marks basically. These pass, these fail. So something like a standard testing kind of an environment which you do. So if the system designer over there, the first programmer, never took into consideration that there can be partial parts of the body. So there can either be the lower part of the image or the upper part of it, then that will create a problem. Yeah, they are all practical things which we need to get into consideration. So I will come to that. That has a very specific name of how to look into whether we did take care of those corner cases as well or not. So now, how the world progressed is something of this sort. So DL is a part of AI, but we need to, yes. So posture realignment is typically I am standing sideways, I am standing say this way, or I am crooked and aligned. Now the point is that all of these over here typically are straight upright. So your spine and this aligns along one single principal axis over there. So you'll have to realign that one. The best way is that you get down your silhouette from chroma clustering, you find out what is this center line over there. So you can use very simple image processing terms like midline transformations or center line fitting or skeletal transformations and get this center line. And then you just realign. Now the moment you realign this line, all pixels and everything will get shifted accordingly as well, and then you will get down a straightened silhouette over there. Are we clear? Good. So if you move and then look into like how the whole world has progressed around this whole thing, you would see that in the earlier days, and this is somewhere in 1930s and 40s, and today it's pretty much there in our lot of devices which we use. In fact, we are pretty much living in an AI-enabled world, which has not come so disruptively that we did not understand, but we are actually living in an AI-enabled world. The first part of AI was essentially what is called as a rule-based technique. There used to be rules. If this, then do that. That's also artificial intelligence because somebody coded that to a machine to do a mundane set of tasks. So take an example of air conditioning machines. You want a set temperature of 25 degrees centigrade. What it does is you set that set temperature 25 degrees centigrade. If the room temperature goes below 24 degrees centigrade, the compressor shuts off. If the room temperature goes above 26 degrees centigrade, the compressor switches on. And it just keeps on doing that. So with a plus minus 1 degree, it's going to twiddle and then maintain the average temperature of the room at 25 degrees centigrade. So this is a simple rule-based technique. You have similar kind of things on your smartphones. So you open up your smartphone and you start dialing, your screen is on. The moment it touches your face and you are trying to hear something, the screen switches off. Because it needs to save on the battery and that time you don't need any illumination over there. So there is just a sensor so your screens today are capacitive sensing ones, which can pretty much feel if there is skin contact over there. If the skin contact feels anything bigger than that of a finger, then it will just shut off the screen. That's it. So that's a simple rule-based technique. You have a threshold. If the contact area is more than this many pixels, then cut off the screen supply over there. Great. But then this was not always that comfortable. I mean, with the AC experience, you know that it's not always comfortable. When it goes almost towards 24, you are actually feeling chilly. If it's towards 26, then you are actually feeling warm. So although the average on a long run is at 25 degrees centigrade, but there is always this fluctuation of 2 degrees centigrade which is happening around over there, and that is not so comfortable for all of us. Now with that, you would see something which is called as a climate controlled AC. So climate controlled ACs are which tune based on what is the humidity, what is the outside temperature, what is the inside temperature, how many people are there in the room, and accordingly it will control at what rate it should operate the compressors over there, and the compressors keep on running. So if you buy a very high-end car, it always comes with a climate controlled AC where you can like set down like, okay, I would like a feel of 25 degrees centigrade in Indian monsoon. So you have those options, small buttons over there which you can set down. So it will maintain the humidity, it will maintain the temperature, because our experience is generally based on what is the humidity and what is the temperature. These two things together make us feel. So you would see on your weather apps, actual temperature is 17 degrees centigrade, feels like 14 degrees centigrade because the air is dry over there. So that's what's happening these days at least. So that was a time which came into this whole thing, that you have your input, but then from your input you find out what is a set of features. So the set of features are what is our perception. Perception is a set of feature. Perception about how comfortable it is. So that's a function of temperature and moisture as well as external temperature. All of these three things taken together. Then you come with something which is called as a learned decision. So what this decision is going to do is that at what rate am I going to switch on and switch off the compressor over there. That is something which has to be learned and that is adapted to you. So it will observe you for a lot of time. You are switching on, switching off, switching on, switching off, then it will come down. Okay, so at this level, this guy is able to maintain a comfort level, and so let me also stick to that. So that's where learning for the first time comes. So it makes errors, you rectify it, it rectifies itself, and accordingly after some time you would see that the amount of error keeps on going down. So simple things. How many of you have tried voice search on Google? Okay. So for the first time when you started speaking on that one, it threw really crappy results. Most of the time it wasn't able to understand whatever you said in English, because it was not tuned to your English. But after some time it gets used to it. And in fact today they have a calibrator over there. It has a sentence which you have to read out, and whether it has been able to detect every single word or not, it will turn the color to green of that whole thing over there. So that's a way of this system to learn, that you are exactly, it's able to understand what you are exactly speaking. Okay. So that's the next part of it, which is classical machine learning techniques of how we developed across the world. Now from there we come into something which is called as a representational learning. Now representational learning was a place where we in fact started learning features as well. So we just did not take some mathematical description over there. So if I have an image, so say let's take the earlier case. In the earlier case what we were doing, we had an image, we found out these features, local binary patterns, wavelets, histogram of oriented gradients, or in the upper case it was chroma clustering and posture realignment. So somebody had hard coded that one. So there was a guy who hard coded every single logic. If the pixel is in this range, this means that. If this pixel is in this much of a distance neighborhood of the other pixel, then that means that. If this is the frequency present in your audio, then this would mean this particular word or not. So it's pretty much hard coded. So then that cannot generalize every single thing, and that's the point where it will fail. So you have seen speech recognition fail because it was pretty much hard coded over there. Now everybody's frequencies are different. I mean, I have a different spectrum of frequency in which I speak. You have a different spectrum of frequency in which you are also speaking. So essentially, though we are speaking the same word, but it would sound a bit different from each other. Right? Are we clear with that? So a hard coding necessarily kills the whole purpose over there. Now there we brought in this kind of a learning of features itself. So what we used to say is, so giving you the example from your phones itself. So it writes a text and you speak that same text over there. So it knows which word you are speaking and it will map those set of frequencies to that particular word over there. Now the set of frequencies is going to be different for different people. So the machine is going to learn, in this case your smartphone is learning which frequency to associate with which word for a particular individual. And that group is going to be different for different people. Now once it's able to identify that this is a set of frequencies which come in this succession, If it comes in that succession, then map it to a word or an output, and that is the learning of decision. I have a set of features. First I will learn what is a feature. Then I will learn if this group of features are present, then it means that this output is being inferred over here. So that's the era of representation learning, which was between 1995 or late 95s to about 2010. Beyond that, we ended up coming into what is called as a full-scale deep learning, a full-stack deep learning, where the whole idea was you give a set of inputs, you know what is your output, and intermediate everything gets learned. But that intermediate point is from a set of learned features, you are going to learn a vast spectrum of derived features itself. So from a feature you can get another feature, from that feature also you can get another feature, and so on and so forth. We'll come into a mathematical form of how this is possible and how it actually works within a neural network. Now where this whole concept of deep learning comes, or a deep neural network, is that you can keep on learning a set of richer abstract features from them itself. So this is not just one layer, but that is a stack of layers over there. So this is where the whole essence comes down. Now essentially if you look into the whole ecosystem as such, then deep learning forms a subset within representation learning, which again is a subset within machine learning, which is a subset within AI. So if you know deep learning, it does not mean that you know all of AI. But if you know AI to a substantial extent, you know a significant part of deep learning as well. So the point is, this whole class is going to focus only on this minor, very minor, compact subset over here, which is just the deep learning part. And we are not going to do everything of AI. So there is a separate course which is running. PPC is taking that along with Orijit. It is on AI foundations and applications. So you can try that one out as well. And if you don't have any more electives, then you can try it again next year, because they would be offering it as well. And that's going to speak about the whole bigger picture of how things work over there. Okay. So I think let's take a 5 minutes break over here, then bio break, and then we get back onto probability and statistics. Okay, so welcome back, and now we are going to take over from here with probability and statistics and how it gets introduced. Okay, now I had started with this whole thing which is called as statistically informed decision making, and the whole essence of this one is from this particular equation, which is also known as Bayes rule. And everybody in this room, I believe, is aware of what the Bayes rule is. That's from your class 11 probability chapter. Okay. Now, in general, a lot of us would also write down Bayes rule in this modified form over here, such that it takes this numerator and writes it as a product of two marginals over here. Now, can somebody tell me what are these things called? Which is called what? Like, what is this part called? Very good. What is this part called? Likelihood. What is this part called? Prior. And what is this part called? The denominator. What is that called? So one good trick of remembering this whole thing is that whatever is the conditional, that should be the probability of the other side of the multiplier as well. So that solves it out. Okay, great. So you have this as the conditioning over here. So essentially P of omega is what you will have as the other part of the multiplier over there. Good. But then what are the names? And the denominator is also a very critical part. And if the denominator does not exist, then nothing can happen over here. So what are the names? So let's get into the names. This is called as posterior. You are correct with that. This is called as likelihood. You are correct with that. This is called as prior probability. This is what is called as evidence. Now evidence is that something can exist. So whether x can exist or not, that is the evidence of that one. So if probability of x is 0, then nothing over here can be solved. Because essentially that would mean that this becomes x equal to 0. This whole fraction over there becomes something which tends to infinity if x tends to 0, otherwise it becomes undefined problem over here. And if this is undefined, then this is also undefined. So now first and foremost, okay, let's get into when is evidence 0. Let's understand the practical implication of that. Okay. I have a 6-faced die which has integers on its face, a dice which you roll. So a dice which is 6-faced and it has integers printed on its face from 1 to 6. What is the probability of getting 5.5? 0. Okay. What is the probability that I roll 2 dice in succession and the average is 5.5? Can you calculate that part? What is the probability that I have rolled the dice twice and the average of those 2 rolls is 5.5? 1 by 18. How did you come with that? So 6 and 5. In the first time it can be 6 and 5. The next time also it can be 6 and 5. So what is for 6 to occur? It is 1 by 6. The next combination has to be 5. That has to be 1 by 6. Okay. So 1 by 36. And this can occur in the other way around. So 1 by 36 plus 1 by 36, that makes it 1 by 18. Good. Great. Good solution. Now look at the difference over here. There was just this framing of a question which is different. What is the probability of 5.5 to occur when I have rolled a dice only once, which is 0? That event cannot occur. That event is null and void. What is the probability of getting a 5.5 as the average if I have rolled the dice twice? But that is a valid event. So 5.5 is not an invalid number. It's only what are the conditions in which things will occur. Now first and foremost point for this evidence, why you need to know this part is that either you, so now in this 5.5 kind of a problem, it does not always imply that you just roll the dice twice, that you will always get 5.5. That may not happen. You just roll the dice once for 2 successions, and then in this particular experiment you did not get 5.5. That's okay. You don't have any issues with that one. I mean, we are not really worried about that. That is because in this particular experiment we did not observe it. But then if we repeat this experiment over a large number of times, at some point of time with a 1 by 18 part of it, it will definitely occur, right? 1 out of 18 times. So in general, if I roll it down for, if I do this experiment for 36 times, I have a chance that twice out of these 36 rollovers it will occur over there. Good. So now let's get into this very simple problem. Now this was what I devised in last year's class. And then last year there was around this time, there was a lot of thing going around with cows in India. And after that, cows are mothers. And now we have mother cows and auntie cows. Okay. With all due respect, I'm not disrespecting anybody. So mother cows are Indian breeds of cows, and then we have imported breeds of cows which are auntie cows. Okay. Aunties are also respected. Auntie from Jersey, auntie from New Zealand. I mean, we have more aunties from New Zealand than from Jersey. I guess so. At least that's what the last survey I read through interpreted. So now if we have that, and then Indian roads are where you will get cows and cars with an equal probability at any given point of time, except for New Year's, because you are and Diwali, when you are blasting too many crackers. So cows will never dare come out over there. Their life, the mother is at risk if she comes out. Great. Now if I give you this simple problem over here, is that devise a system which will use very low cost sensors in order to say whether there is a cow or a car in this part of a particular part of land. So say if it's a playground for kids to play around, and if somebody is driving a car over there, that is prohibited. But if there is a cow which is grazing, that is not prohibited. Okay. So how will you identify whether there is a cow or there is a car? Oh, but then we have those weird kind of horns as well. That's a very good trick actually. You can do an audio detection and then look at the spectrum and then find out. Good. And what more? But say it's thundering or it's storming, then it becomes problem. But then you will have to implement a vision-based solution for that. So if I am implementing a vision-based solution, I can pretty much do a template matching, some sophistication thing. But I don't want to deploy a camera. I mean, where will you put a camera in the middle of a playground?
inductive loop antenna over there to do that. Imagine what will be the size of the loop. Sonar, okay, good idea. What will you do with sonar? So who said sonar? Somebody said sonar. But sonar is the answer. I mean, that is at least what I am using over here. So we did a very simple thing over here, very straightforward. You have those Arduino rangefinders, ultrasonic rangefinders on Arduino, which cost about 50-60 rupees or something. Okay, you take that rangefinder and put it, and you put a small LDR, light detecting resistance over there. Okay, what this LDR is going to do, based on whether one is positive or negative coefficient, whether it's bright light or dark light, is going to just change the sense the shade of gray, shade of intensity which is present, whether it's bright or it's dark. Okay, if I'm just going to measure these two things, and I want you to devise a mechanism by which you can comment whether this is a cow or a car. Now look at the problem. The problem is that a cow ranges from anything in a shade of bright to a shade of dark. A car can also range in the same way, and because it's just sensing the intensities, not looking at exactly colors, it's just looking at intensities over there. So it can be anything over there. Next is that the length of a cow and length of a car is almost the same. Maruti 800, which you guys haven't seen possibly. Then which car? Hyundai i10. And Nano is smaller than a cow as well. Nano is pretty much, you can say, like the size of a calf or a donkey or a mule kind of a thing. It's a like real cute design. I mean, I sat inside a Nano and actually I fit inside a Nano. That was weird part of it. I could not fit myself inside a Maruti Suzuki Zen or a Maruti 800, but I can fit myself inside a Nano. So the point is that there's a bit of ambiguity which will come. You cannot have a straight decision over there. You can go to the other side of it, which is I will use very costly cameras and I will take images and then from there I will do it, but then it increases the cost. Now imagine this, your camera costs almost like buying 300 Arduino kits. An Arduino kit is just 300 rupees. The camera for any, I mean even this webcam with which we are recording, that costs 10,000 rupees. So it's going to be significantly higher. If you are taking those surveillance cameras, they are even more costly. So the problem is that on an engineering side, you can start with low cost, but then you will have to augment everything with your computation on the other side of it. Now let's take this problem, and what we do is we observe at a given point of time, at a given spot, what are the, for say 1 hour time, we just counted every single cow and car which came, and for every single cow and car we measured what is the shade of color from bright to dark. 0 means brightest white and 1 means dark black, and we also measured its length of that object over there. Okay, and this is what I get down. So this is essentially every single point where you have a cow or a car, that is an icon which I put at that particular location of wherever the value is. Now can I use this information and this whole thing in order to come to a decision of like where in what measurements would there always be a cow and in what measurements would there always be a car? Decision boundary, how will I get that? So now look, so we will come to that. Like somehow if you are able to evaluate these parts, that how is in the next part. If you are able to evaluate that part, what will happen is you get down this probability of omega is equal to omega. This small omega is either cow or car. So say small omega 0 is cow, small omega 1 is equal to car or something of this. Now wherever the probability for cow is higher, you would say that part belongs to a cow. Wherever the probability for car is higher, you will say that part belongs to a car. Now that can be mathematically written in this form which is called as the maximum a posteriori estimate or MAP. And we have at some point of time all heard about what is MAP, a maximum a posteriori estimate. Okay, so I just have my posterior probability calculated, and then I say based on my posterior probability what is my estimated class over there. Now once I am able to do that, this will end up giving me something like a boundary over here. So this boundary says that anything above this boundary is always a cup, so you will always find cars with the highest probability. Anything below this boundary is what you will get down as a cow with the highest probability. We agree on to that one. This boundary is what is called as a decision boundary. So this is what divides the decision. This is the boundary between the two decisions which I am going to take over here. The question is that there is a lot of challenges associated with this decision boundary itself. First is if I have a lot of samples. So now this is just a generalized representation, and then I have two classes, no more cows and cars, but some two classes of objects. One is a red circled class, another is a green square class, green plus class over there. Okay. Now if I have abundant number of samples, then it would be very easy to construct this decision boundary over here. Great. But this would mean that every time I have some samples based on which I am going to make a decision, I should have abundant number of samples, which is the ideal case. I would always need that. However, in real life what will happen is you will not get that many abundant number of samples. Now here you can either have this, okay, or you can also have this. Now see, both of them are going to satisfy the conditions of a decision boundary. Which one do you think you are going to choose? No, left one is what is ideally going to happen. Over here, one option is that you can have this kind of a crooked decision boundary, or you can have a straight line as a decision boundary. So which one out of that, curved decision boundary or straight decision boundary? Straight line. Okay. Then you are saying curved. Okay. Now the problem is, here if I look into this whole problem over here, I will have some performance measure based on which I will say that this is my good decision boundary. Now this performance measure, if that is mean square error, you would see that the mean square error for this straight line is going to be the lowest when you don't have abundant number of samples. Now going by that rule, you will vote in favor of the straight line. Now there is a reason why it will be having the least mean square error, and why it will be easiest to find a straight line as well. That I have in the next slide. There is a mathematical reason why that would be easiest. But now that we have voted in favor of this straight line itself, comes another big problem, which is the scarce sample problem, where you have even lesser amount of sample, which is in practicality what will happen. So today most of you are how many of you have already attempted doing something with machine learning or deep learning? A lot of you. And in most of the cases you had just 10 samples, 20 samples or 100 samples. Yes? And then you thought because everybody is beating a gong around with deep learning, so we will put a deep neural network with 100 samples and solve it out. So today we will learn exactly why we should never use deep learning if I have 100 samples. Never ever. The problem is, if that 100 sample case or 10 sample case is this. You have scarce samples, much lesser number of samples. Now you chose this straight line because this was having the least error. Now if you put that straight line, this goes over here. But then this can also be another option which will give you minimum mean square error. This can also be another option. This can also be another option. Now which one will you choose? None of them. Everything has the same mean square error. That's with support vectors. I am just doing a single margin, like a linear discriminant analyzer, an LDA. Now which one will I take? All have the same mean square error. This one, this one, this one. Any one of them. That's the main problem. So we basically have to choose any one of them over there. And the whole reason why you having less number of samples will never give you great performance, because the point is you trained a model on this one, you want it to get deployed on this one, and the ideal decision boundary is supposed to be a curve and not even a straight line. So one is you chose a very non-optimal solution, your straight line was not at all optimal. On top of that, you chose a suboptimal straight line itself, which cannot do that decision over here. Now, if I try to fit this straight line over here, you know that there is a significant amount of error which will come down. So that's the primary problem which will happen. So we need to be really careful about the quality of data. And in general, we need to have this kind of a data, but that's one of the biggest challenge which you will face over here. Next is, for this particular challenge, let's look at what will happen in terms of a statistical decision making. So one is I can have this kind of a line. Now if I have this kind of a line, which is a very good separation boundary over here, then that would follow down something which is called as a cubic equation. And that's not so hard to understand. I mean, you have 2 points where your curvature changes. If there are 2 points of curvature change, it's a cubic polynomial. If there is 1 point of curvature change, it's a quadratic. If it's no change, then it's a linear polynomial over there. Great. So now, this boundary is cubic over here, which means that this posterior decision over here, this polynomial is also cubic. Now this polynomial can be cubic only if this whole fraction is cubic. Now the fraction is cubic when either this one or this product is cubic. Okay. Now let's do a dissection over here. This part, what is this called? This probability? Prior. That's a constant number that does not have a polynomial function. This part is likelihood, which may have a polynomial function, and in general we'll go by some distribution model and there will be a polynomial function. Now if this is cubic, because the summation of this marginal is what comes in the denominator as your evidence, so that is also going to be cubic. So if numerator and denominator both are cubic, then the polynomial itself is also cubic. Okay. So now we have a cubic polynomial because the likelihood which we modeled over here was cubic. Okay. Now from there, even this would also be a fit, and this is a quadratic polynomial. This to a certain extent will also be a fit because you did not exactly misclassify these two. You just grazed along the border over there. So 3 of them are equiprobable. But then let's look into the computational complexity associated with them. For this linear one, linear is y equal to mx plus c. How many free variables do you have? M and c. There are 2 free variables which you will have to train because x and y comes in a tuple, that is a combination which is given to you. You just have to find m and c. Right? For a quadratic, how many free variables are there? No. For a full scale quadratic, ax square plus by square plus cx plus dy plus exy plus a constant f. So you get 6 over there. Similarly, if you go for cubic, I think it comes to 16. So because you will have a coefficient with x cube, y cube, you will have with x square, y square, xy, then you will have x square y, then you will have xy square, then you will have xy, and then you will have a constant over there. So just sum it up, it's 12 or 16 something over there. So the more you go on these models, you will keep on increasing your parameter space over which you would like to optimize. So your model complexity increases in a very significant way. Okay. Now, where does that relate to in a practical sense? So if my number of free variables are increasing, is it good or is it bad? And then what do I need to have in my data in order to be able to fit that model? Because you will need unique number of equations. So if I have 2 variables to solve, I need 2 equations. If I have 6 variables to solve for, I will need 6 unique equations. If I have 18 variables, I will need 18 unique equations to come down over there. And on top of it, we are looking at a mean square error kind of a solution. So it's not exact match, but it will be a almost approximate match over there. So again your statistical rules of that you need to have statistical sufficiency, which is at least 30 independent equations which will come to a convergence point for one variable, that should be there. So what that would bring us, if I have d number of free parameters, then I need 30 d number of unique equations, which would mean that I need to have 30 d number of samples present at least in my model. Good. Now let's get to a deep neural network. A standard deep neural network, say VGE net. has about 100 million parameters. 100 million parameters, you took that one up and now you want a training data. So that would mean 33,000 million parameters, which is 3 billion samples to solve out. 100 billion parameters into 30 is 3 billion. So you will need 3 billion samples. Does your data set have 3 billion samples? So you have an ill-posed problem. You have a significantly ill-posed problem, and this is where you were lost. Okay. Now, why that happens is over here. So if I take the simplest of the model, say I have limited amount of data, let me take simplest of the model, and I will do it. In that case also, the problem is this line equation, you can have multiple number of solutions which will come around this line equations, and all of those solutions are going to be equally probable. So now we need to have something which is called as a domain knowledge, which comes into this place, where you know exactly which of these line equations should you do. Now if I come from that domain knowledge and I say that okay, these are sparse and spread across, but then let's have a line which is almost centrally placed in between both of them along that gradient. So it rules out this part, it will rule out this one, it will rule out this one. Maybe this one is a good assumption because it's almost centrally placed from both of them, so it will make errors on both the sides of it. So that again depends on whether I want to be biased towards the positive class or negative class. If I want to make more errors on positive or negative, it depends on that. Now, as human beings, we also make that kind of decisions. Okay. So say, how many of you go to a chemist and not to a doctor when you have a fever or a sore throat? Before you came to IIT, I mean, here in BCRI you will always get a doctor, so you always go to the doctor. Because until that guy writes, you will never get a medicine. But then outside, how many times did you go to a doctor when you had a fever, sore throat, or say some pain in the stomach? Most of the time it would generally that you go down to a chemist and tell him that this is the problem, get me a medicine. Okay, why was that? Why did you do that? That was easiest basically, and it was cheapest also. It's economical in terms of money and time in both the ways. Okay. Now, what was this guy doing? How does he select? The chemist is not a doctor. So how does he know what medicine to give you? Huh? From his experience, and there are some beliefs which he has. The belief is very simple. If most people are having dengue and you have a recurring fever over there, give him dengue medicine. If this is monsoon and there are lots of mosquito bites going on, and he has a recurring fever, then this is definitely malaria. Give him medicines for malaria. So these beliefs, and in fact a doctor also goes with these beliefs. You would see a doctor is going to ask you these mundane set of questions. So for how many days did you have the fever? If you say 1 day, then he is going to give you some just normal reliever and then say after 3 days you go and do a blood test, because only then we will get to know what is the actual scenario over here. So there are these kind of beliefs, and those beliefs are such that nobody gets penalized. Okay. So one point is that a doctor will be able to treat people to the best way, that he keeps on giving every time a medicine for malaria if a person comes to him for, if a person just turns up to him, maybe doesn't even have fever, nothing, this guy just came over there, a healthy guy who comes to him and says like, can you do a checkup and find out if there is some abnormality in there? I mean that's a name, that's a standard practice which is called as preventive checkup. In fact, I get that done as well. So I go to my doctor and say I am healthy, but you still need to find out if there is something underlying which is going wrong over there. So now if this guy keeps on regularly giving me malaria medicines every time I turn up, now definitely no person who has malaria will be left out. They will all be cured. But then there is a bunch of people who never even had malaria and you started giving them malaria medicines. Why? That does not mean, I mean, that will have some side effects and something. So that's the type of error, whether you are unbiased on both the sides or you are biased with certain number of people. That will also have its own impact. Now that's something which we need to really take into consideration over here as well. So for machine learning in general, there are 3 primary objectives which we always look into while solving these kind of problems. One is the data, and that's where if you have a lot of data, that is the easiest problem to solve. If you have less amount of data, that is the most complicated method to solve. So less data is never the easiest one. Remember that. It's an inverse rule. Less data is the toughest one, because now you started with a linear model, but you don't even know which is your best linear model. Now here you would think that it's a cubic model, but then you know that the cubic model makes the minimum amount of error as well. So the mode data case is actually a good one. Now the challenge is, how do you come from this to this? That we will eventually cover. The other one is what is called as a model selection problem over here. So in the model selection problem, what happens is, the easiest is obviously a linear model. Complex are cubic because you have more number of free parameters, free variables to tune over there. Good. And that's how your complexity will increase. And in general, you would try to represent any of your problems in terms of linear, because that's going to be the easiest to solve. The last and the most important part is what is called as the control plane of the problem. How many of you love control systems? One guy. Nobody else raises their hand. In fact, I was also terrified of control systems. So the point is, what this whole thing over here, where this whole thing of a control plane of the problem comes into, is something of this. I have this model which I need to fit onto this data. That's the objective of machine learning. Now there has to be a way in which I define what is called as a fit over there. That's something which I do with this whole thing. Now the simplest one is something which is called as a maximum likelihood estimation, which is that base problem. So I have a probability definition and something, and probabilistically I am able to fit. The next one comes down what is called as a mean square error, and this is a standard regression problem. So starting from your class 10 level regression, you have solved a lot of regression problems. In physics labs you had to draw those trend lines and everything. If it's a linear or quadratic or cubic, you used to do, and the main measure over there was whichever gets the minimum mean square error over there. From there we come on to what today a major part of the world does, is what is called as perceptual loss. A perceptual loss or a perception loss is something where you don't have a mathematically well defined objective available to you in order to say that this model has fit onto this data. But then you have a perception associated with it. So a person can look and say, okay, if these things are maintained, then this model is fitting on this data. If that is not maintained, then the model is not fitting on the data. So let's get one by one. Now this problem is always going to be there. It's not that you can overnight come from here to here. Some of these are, say that if we are solving a disease identification problem, and there is one disease which happens in 1 in a million people, which would mean that if I need at least 300 people data, I will have to wait for 30 years, something of this sort. So there will be a time implication and something which becomes very impractical in that way. Now how can we get around? So one way is say we were solving one of these problems which was for WBC, and this was in a super resolution problem. That's also there. We'll come to that super resolution work which we had done and how we did. Now there was this whole problem that WBCs or white blood cells are much lesser than red blood corpuscles in your blood. Now as a result, if you take an image of a blood smear, so has everybody got a blood smear done at some point in life? Blood smear, malaria test, even your admissions need a blood smear, right? They prick a small dot over here and then take a drop of blood on a glass slide and then smear it out and then looks under a microscope, and then they tell like this is your RBC, WBC, blah 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 blah, and you are healthy, unhealthy, and every time the report is healthy. Because if you are unhealthy, then they will not give you admission. Okay. Now here, if you want to do that and say I have these WBC images present over there, the problem is I have less number of WBC images, but then these cells, they are circularly symmetric. I mean a cell, if I look at it from this way versus if I rotate it, it's still the same cell over there. It's just some rotation which comes down over there. Okay. Now essentially this and this will have the same pathology, same information and everything over there. But then the moment I do this kind of a change in the feature space, this might lead to a small shift, like from here it might shift over to here or here or here or here. Some small shifts will be around over there. So by doing this kind of say rotation, flipping along up down or flipping left and right, I will be able to get down some small minor jitters which I create around that. By way of creating these jitters, I will be able to create a much denser space which looks almost like this. Right? Okay. Now this is what is typically called as augmentation or data augmentation. Might have heard about this one. that you need to augment your data if you have less amount of data, and this is a typical data augmentation thing. Now this is a very good paper from where you can read about these different things of data augmentation, and generally it's an art and not even a science. The reason for that is you can do all of this on WBCs, but please don't try to do that on the cow, because if you end up doing a flip up down cow, how many times in real life will you see a flipped up down cow? Who has seen a flipped up down cow? Let's ask. No. No, in real life, have you seen a flipped up down cow? Have you ever seen it? So the chances that your vision system in real life will actually see a flipped up down cow is null. So this is a condition which will impose a point where evidence is going to be essentially zero. No. So here is like, this is one example where I was showing that if I have less number of WBCs and more number of RBCs, then I can do all of these rotations, augmentations in order to get that. Cow can be augmented. You need to augment the cow as left, right. So now in a real vision system, in the real world, will you see a up down cow? So practically the evidence of getting an up down cow is zero. So if a particular condition is never going to occur, which I know from a statistical information, I should not have that in my augmented data, because augmentation is essentially where I am synthetically imposing some data. Now that synthetic imposition should not bring in some adversarial data over there. Then I am going to jeopardize the whole learning of the system over there. That's the point. So the whole objective over here of giving this example, that you need to really look at this as an art of augmentation. And this is not just a science where you write down one. So if you have a data augmentation code for WBCs, don't vanilla implement it for cows, then it will not work. Yes. The point is that here we are looking into a vision based system. If you invert a cow and you are looking into that earlier problem where I am just measuring shade and length, that is not going to change. Even if I do a flip left right, that will not change. So essentially these point in feature space are not going to change in that problem. So this augmentation is also very specific to which problem I am looking at. If the augmentation does not lead to a shift in the feature space, then it does not have any implication. In fact, in some cases, we forcefully make a feature space where the augmentation will not have any impact as well. So when we enter multitask learning, I will give you examples where we forced a system that I will augment the data, I will introduce changes in the data, but you cannot have any changes in the feature, and you will have to make yourself learn those kind of features as well. So it's very specific to what I am going to train and what is my objective over it. So it might be that I want to get rid of adversarial attacks. So if there is a so it's like you, even if I am taking your side view, is still the same person. So if my features are still the same for any views of you, then your system is going to have an independent of that one. Now it sits on what is my motive. So that task has to be defined, and this augmentation has to be linked to that task itself. Now from here, if we get into the next part, which is the model selection part of the problem. Now in model selection, the easiest is linear. Okay. Now let's take an example like this. Now here, whatever features you have learned, say those features look like this. This is some arbitrary x1, x2 features. Okay. Now here obviously your decision boundary, if you look at it, that's a quadratic one. If I ask you, can we do something, can we put another layer over here, and that layer can have some mathematical transformation over this feature such that this decision boundary changes from quadratic to linear. So can you tell me what should be that kind of a transformation we need to implement? Distance from the center. So essentially if I do a polar to a Cartesian to polar formation, so I represent this in term instead of x1, x2 in terms of r theta format, then I should be able to do it. Okay. So now if we have this kind of a model which has an abstract features, and this abstract feature is convert a Cartesian to polar domain, then I will end up getting this sort of a line which now becomes a linear degree 1 polynomial. Now the whole part of deep neural networks and why they have been so popular is because it breaks down a very non-linear problem into depth-wise linear problems. The whole point is just to break it down into a set of linear problems. By way of doing this, what it's able to do is every single layer has less number of parameters than the cumulative parameters I would have needed. So it makes every single layer easier to train. Now look at the point. My limitation is not the total number of parameters needed by the model. My limitation is one single layer which I am optimizing at a time. What is the total number of parameters? So I will need that many number of samples over there. So the design of a layer itself is a very critical task. And when we go deeper and deeper into the whole subject, we will come down that the same task can be solved with much significantly lesser number of parameters because you have been able to intelligently engineer each of these layers itself. Now the last part is on understanding MLE to what is a perception loss. Okay. Maximum likelihood estimation with that Bayes framework is what we are all aware of, and we have done a good amount of it. The point is, now if we come down into this whole point of, say that I give you this sketch of an image and there is a CNN whose job is to take this sketch of an image and generate something which looks like a photograph, a real photograph. Now if this generates something like this, that does not look like a real photograph in any way. So typically the mean square error between this and this is very low, but then the perception that this is a photograph is not there. So essentially a loss associated with that perception is also very high. Instead of that, if I generate this one, this looks very much like a photograph, and it looks very much like a photograph of this house because it has that curved roof, it has that chimney, it has this porch, it has that one door. All of this is present over there from some other orientation, but it's of the same house. Now if I tell you that this is the photograph of the house which is over this sketch, then the perception loss is pretty low. But then if you try to do a mean square error, pixel to pixel mean square error, that is very high. So now you can pretty much see that if we have this kind of a problem where I am giving a sketch and getting a house, mean square error is not at all a metric which you can use for solving this one. And you have to really dump it up. I mean today people, the last time I heard even Andrew Zizerman was speaking the same thing in December. He said like we should take mean square error and dump it in the dustbin. This was a good statement. I really love that statement. Mean square error is not going to solve all of your problems. You really need to understand. If you have a regression problem which you are trying to solve, it's good. But in general, we are not always dealing with regression problems. We have these kind of classification problems or perception understanding problems where mean square error will not be of any use. So the problem comes in that I have perception, but then how do I model perception as a loss? Now there comes in this kind of new ideas which we have. We use a neural network in order to understand and model the loss function itself. Yes. And how that is done is through a trick. So what you do is, you have a neural network and you tell this neural network that I'm always going to give you a pair of images. One is what is generated from here, another is an actual photograph. Your job is to learn to identify a real from a fake. So anything which comes from here is a fake, anything which comes from an actual photograph is a real. Your job is to just identify between these pair which is coming in. By way of doing this whole thing is going to be able to understand what are those nuances of these differences between them. Great. So essentially it has been able to understand what is the perception between an actual photograph and a real case. An actual photograph and whatever is fake over here. Now if I tell this one to modify its performance such that it can minimize, such that it can maximize this loss. So when can this loss be maximized or the performance of this one degrade is your photograph is never going to change. That real photograph will always keep on coming. This will start getting confused only when whatever you are generating looks like a photograph. Right? So by way of doing this, this will start generating images which look more closer to a real photograph and not something which looks like a sketch. So and that's the whole point of what today we call as generative adversarial networks or adversarial learning in general. So an adversarial learning essentially tries to do. The only difference is that this main generator over here itself is the adversary, because this is trying to fool this guy over here. such that this starts believing that whatever it has produced is actually real and not the other way around. And there is an immense implication which this has produced in the field. So we'll get in how this has really improved our ways in which we are able to do semantic segmentation, scene understanding, then understanding saliency of images, including generations as well, not just generating. Okay. So from there, if we look back, so we're at the verge of it, so I will not do this one. This is what we will start next day. So we'll start from that you have a data, and how do you go from that data into statistics, and from statistics how do you understand the information theory itself. Okay. So we again meet tomorrow at 10 a.m. in this room.